Yeah, thanks, Jenny. Thanks for inviting me. So this slide will be well known to many of you, but let me start there nonetheless. So if you would look at the visible matter on the night sky, estimate its mass, and apply the laws of gravity, whether Newtonian or Einsteinian, to try and predict its behavior, then you're going to get the answer horribly wrong, and the problems appear at a range of scales. So at the smallest galactic scales, you would expect that the galaxy rotation curves are going to decline. Turns out they stay flat. The level of galaxy clusters, turns out that the velocities of the galaxies in the galaxy cluster are much stronger than you would expect. The same for gravitational lensing, whether that's of galaxies or galaxy clusters. Again, you see much stronger than what you would expect based on the mass of visible matter plus standard gravity. And also at the largest cosmological scale when it comes to structure formation, which you can measure using this little graph of the angular power spectrum of the anisotropies of the CMB. And it turns out that structure formation has developed much more than you would expect based just on the visible matter and its mass and the laws of gravity. Right, so visible matter plus gravity doesn't get an effect that's strong enough. So there are two options, logically speaking. Either you need to add more mass, but we can't see it, so dark matter, some form of dark matter, or you need to modify gravity, enhance it. And that's often done, at least in the pre-relativistic regime, by something called MOND, where you boost it not on a certain length scale or velocity scale, but if the acceleration is below a certain value, A0. Right, so most physicists go for the first option, the dark matter option, usually a particle form of dark matter, whether it's axions or neutrinos or WIMPs. And as I said, the modified gravity people go for something like MOND and then to try to find a relativistic extension. And dark matter, or theories that label themselves as dark matter, tend to do very well at the large scale, so the cosmological scale, the galaxy cluster scale. But at the galactic scale, there's some so-called small-scale problems, where if you try to simulate structure formation, then you don't get the number of all the different types of dark matter halos correct. MOND, on the other hand, is quite successful at the smallest scale, the scale of galaxies. It's very good at predicting, explaining, accounting for various astrophysical correlations, such as the Taylor-Fisher relationship, which correlate the baryonic matter, the visible matter, with the mass discrepancy, although of course they wouldn't call it the mass discrepancy, but the modified gravity effect. However, modified gravity theories are typically either silent or very bad at predicting or accounting for the larger scale observables. Okay, so basically you have two communities, or like a cluster of dark matter communities perhaps, and modified gravity community, and the first cluster is by far the biggest. And it would be quite an understatement to say that these two communities don't get along at all. There's an enormous divide. There's barely any training zone, a term coined by Peter, right, where the two communities, even if they have different languages, would come together to using a contact language to trade, to exchange solutions, etc. Tools, methods, etc. You might think that is very important if you want to have probes in science, that all these different communities, in some sense, glued together, not totally isolated from each other. But in the case of dark matter and modified gravity, that doesn't seem to be the case at all. Many of you who have spent time with both these types of physicists might have noticed that. There's it's very polemic, a lot of frustration, things can get very intense, and often referred to as different paradigms. Both sides accuse the other of being very dogmatic. And it seems to be this idea that both sides, that for their side to be right, to win, the other side must lose. It's one or the other. These things are mutually exclusive, and to some extent they're enemies. And then I think if there's supposed to be a training zone, there must be some common ground. And often it seems like common ground is very difficult to find. So kind of big framework, one of the main overarching motivations for what I'm going to talk about today is trying to understand this relationship between these two communities. And I think there are at least four sides to this story. The first obvious side is empirical data, basically what I said before, and is of course very important and what physicists most explicitly talk about. But I don't think this can be all of the story, right? As I said, although both camps often say, oh, we're doing very well, we've accounted for everything. I mean, I think it's fair to say that none of these two camps has currently accounted for everything, right? The dark matter has small scale problems, modified gravity does very bad at a large scale. And then sometimes they might say, well, but at least dark matter or maybe modified gravity accounts for 90% of the data, the most important data. I'm not sure what to say about that. I don't really know how to quantify this data or say that. But in either case, anyway, both of these groups are very smart people. They all have access to the same data and nevertheless disagree on what's the right approach to take. So I contend, and I know this is controversial, so we can discuss this more during Q&A, but I'm going to assume here that there's both communities have something of value to offer to the other community. These the particle physicists, the cosmologists who are into dark matter have loads of value to offer, and the observational cosmologists, the observational astronomers, which to some extent overlap with the Mondians, have loads of interesting astrophysical correlations and phenomena to emphasize and to bring to the table. Although often, as soon as they mention the word Mond, people don't want to interact with these things as much, but I think there are some interesting astronomical phenomena there. So I think there are more sides to the story to understand how these communities interact or fail to interact. Another thing is kind of social factors. It seems that different communities find different exponenta, different patterns in the data more important. They prioritize them. And to some extent, I think this might have to do with which department one is, right? Whereas if you're in a particle physics department or a cosmology department, it seems more likely that you're going for the dark matter approach. Whereas Mondians are often, you find them more often in observational astronomy departments, or at least that is the working hypothesis. And to try and substantiate that in a kind of quantitative, large-scale, systematic way, I'm working with Sophia Houde, Daria Drevkic, and Adrian Wuttrich on analyzing this with tools from the digital humanities. Then I think the third part of the story is that it seems that both camps have different explanatory ideals, different ideas of what it takes to provide proper explanation, not just fitting the data, but a real explanation of what's going on. And it's then not surprising if both have different explanatory standards, different measures of success that each camp can think, oh, well, according to my standard of success, I'm doing very well, and the other program is not doing so well. But if both use different standards, then they're kind of talking past each other. I'm working on this with Martin King, and the working hypothesis there is that dark matter side focuses more on unification. That's more important, whereas modified gravity advocates emphasize simplicity. And then I think the fourth part of the story is the idea that the question of whether there is a strict conceptual dichotomy between dark matter on the one hand and modified gravity on the other side. And by that, I don't mean whether you could add a bit of dark matter to the universe and modify gravity a bit, but whether if you postulate a new field, whether that field must necessarily be purely dark matter or purely a modification of the gravitational structure, or whether it could be a bit of both, or maybe even neither. Yeah, so since this is the foundation seminar, I will be focusing on this part of the story. Even if you don't care at all about communities, how they interact, I think this part will still be of interest to people interested just in foundations, right? Because here we're trying to get, even if you would be only interested in dark matter, I contend that it's still useful to figure out what dark matter is by seeing how it compares to other supposedly different approaches like modified gravity, to get a better grip on what this dark matter concept is supposed to be and whether it's really distinct from modified gravity or not. And this is work with Dennis Lehmkuhl, and all the details are in these two papers, and I'll highlight some bits from these papers. So what I'd like to do today is focus on a very small recent trend of what I might call hybrid theories, theories which try to use elements both from the dark matter side and the modified gravity side. I'm not claiming this is a huge trend. I'm not saying this trend is necessarily going to change everything, but I think conceptually it's very interesting and potentially also heuristic in the sense that it might give us hints about how to for theory development in the future. So basically, and I'm going to focus on one of the most popular ones, that is the superfluid dark matter theory by Lascia Biaggiani and Justin Cooley from a few years ago. So basically what I think we'll learn from this theory is that it tells us to push back a bit against a tradition that started with Democritus, right? Atomism, everything is either the void, space, or atoms, so matter. And then ever since Newton, this conceptual dichotomy reigns supreme, right? Either you have something, an object is either Newtonian spacetime or it is Newtonian matter, for instance, in the form of point particles. Yeah, this tradition seems to say, well, everything in the universe has to fall on one side, either the matter side or on the spacetime side. And for the purpose of this talk, I'll just take spacetime and gravity to be two sides of the same coin. Right, this tradition is also encapsulated in the famous container metaphor, where spacetime is the container and matter is the contained. And what goes along with this tradition is the idea that you have one separate space of spacetime / gravity theories and one separate space of matter theories, right? So you have a whole class of dark matter theories, for instance, and a whole class of modified gravity theories. These are just two separated groups, spaces of theories. Okay, so what I'll do in a second is look at this superfluid dark matter theory, where there's one new field being postulated, and try to ask, is this field really just purely a modification of the gravitational structure of spacetime, or is it purely dark matter, or maybe a mix of both, and if so, in which sense? Before doing so, I'll need to tell you something about how we go about defining the concept of matter or dark matter, and after that, what we mean by spacetime or gravity. So here are some criteria in the literature for how to define what matter is in increasing order of logical strength, right? So the weakest criterion you can think of is this, whether something is dynamical or not, right? To be matter is to be dynamical. In the Newtonian context, that's enough to distinguish space or spacetime and matter, right? Newtonian spacetime, not dynamical. Newtonian planets are dynamical. Okay, that's enough to distinguish the two. Sometimes a stronger principle is brought forward, action-reaction principle, right? Everything that's acted upon reacts. The next stronger principle would be, well, can we associate with those actions and reactions a form of energy? And we already see that that gets interesting if you try to figure out, okay, so the metric of GR is that normally we think of GR as our spacetime theory, but is the metric really spacetime, or is it also in some sense matter? And if you think to be matter is to carry energy, and you think the metric of GR carries energy, then it seems, oh, well, maybe it's spacetime, but it's also matter. Of course, in the case of GR, that's quite controversial. Feynman and Bondi thought, well, yes, it carries energy because in principle, gravitational waves could heat up sticky beads and shatter the rock of Gibraltar, whereas others, of course, have pointed out, well, gravitational energy can be represented by a tensor, and best pseudo tensor, so it doesn't count as energy. So a lot of controversy there. I won't dwell on that right now. Let me just briefly mention that the strongest criterion you could think of is mass, right? Newton thought that's what matter is. It has mass. So you might think not only do we say to be matter is to carry energy, but you also might want to insist that part of that energy is due to rest mass. Although I'll say immediately that's probably too strong, right? Because photons, we tend to think photons is matter rather than spacetime, and photons don't have mass. So maybe mass is too strong. Maybe energy is a better way of defining matter. Okay, now let me say a bit about how we might define spacetime. What's on this slide is not the only way of defining it, but I think together it might be jointly sufficient set of criteria for something to be spacetime. So often we talk about a mathematical structure representing spacetime, something like a differentiable manifold with a connection or a Lorentzian metric, or maybe just a conformal structure. But that's just a mathematical object. How does that get us to physical space, right? You could also use this to represent the configuration space or what have you. So we want a bit more than that. We want to check whether both test particles and light rays follow the GD6 of that single metric or conformal structure. Right? If they both follow the GD6 of the single family of GD6 corresponding to one metric, you might say, okay, that's the space-time, the metric, the conformal structure they experience. That gives us some reason to believe that that's the space-time in the theory or the possible world we're looking at. And you want to also try to check something else, right? You might think paradigmatic spatial-temporal behavior is how rods and clock behave. So you also want to check that special relativity is locally valid, that there are no curvature terms causing trouble, and that locally rods and clocks behave the way you would expect from special relativity, right? So this is if there's some object, some metric or conformal structure, and rods, clocks, test particles, and light rays behave in an appropriate way with respect to that structure, say, okay, that's good reason to believe that has picked out the physical space-time, that theory, or that model of the theory. Okay, So what I've done is I mentioned some criteria for matter in the literature and some for modified gravity / spacetime. So now let's look at this hybrid theory, superfluid dark matter, and then I'll use these criteria to evaluate whether the new entity postulated by these theories is dark matter or modified gravity / spacetime, or maybe both. So Biagiani and Khoury agree with me that neither dark matter nor modified gravity has won everything as it stands. Both got part of the story right, and they want to develop they have tried to develop a hybrid theory that is supposed to be the best of both worlds, the dark matter world and modified gravity world. So what's wanted here is a single new entity for which there is a very natural reason such that on large scales, cosmological galaxy cluster scales, it behaves like dark matter somehow, but whereas on the galactic scales, it behaves like modified gravity. And there's a relatively easy solution for that, namely something called superfluid dark matter, right? If you have a new field, it can be fermionic or bosonic. If it's bosonic and some few other conditions, then there will be a critical temperature such that below the temperature, it forms a superfluid Bose-Einstein condensate, right? Now, if this is a massive field, it's not going to be able to mediate long-range force. But if it's below this critical temperature, which it will naturally happen if the conditions are right, then this field will condense into a superfluid phase, and you get superfluid sound waves, phonons, and these are massless. So these can, in principle, mediate a long-range force, and hence could, in principle, modify the gravitational structure. So that's exactly what they do, right? They postulate a new massive scalar field, a boson. This is the picture here. Unfortunately, the black is not actually the dark matter, but the baryons, and that's somewhat unfortunate. So here, above the critical temperature, the blue particles, that's a new field. This will just behave like, for instance, like axions, and will gravitationally interact with the black baryons. Now, if you choose the mass such that it's quite low, then in certain regimes, like in the center of galaxies, where the density is high enough, the de Broglie wavelength will be large enough, larger than the interparticle distance, and all these phonons will start to overlap. If you give it enough time to thermalize, these phonons will cohere. Since they're massless, they're able to mediate a long-range force. If you then choose the right equation of state, the right kind of superfluid, you can pick it in such a way that the long-range force they mediate is that of modified gravity, right? So basically what happens in galaxies is that exactly those conditions for superfluidity, right, happen in the center of galaxies. The temperature there is lower than the critical temperature, and you get the superfluid there. And hence you get phonons which mediate a Mondian force, which is exactly where Mond effects normally happen. So that's exactly what you want. Okay, so how should we analyze this theory? Is this new object, this new field, matter, dark matter, or modified gravity? Well, in this slide, I'm going to basically summarize 20 pages of paper, so all the details you can see in the papers. But basically, this new field postulated by superfluid dark matter is as much dark matter as anything could be, right? It's quite easy to see in just that it has mass. It's a massive field. And what's somewhat more difficult to see is that at least in the superfluid regime, so in the center of galaxies, it's also actually as much of a modification of the gravitational structure of spacetime as anything could be. It's a bit more difficult to see, but the reason for this is that where normally in GR, the baryons would couple to the Einstein metric, the theory here is such that in galaxies, baryonic matter actually couples not to the Einstein metric, but to an effective physical metric, which is made up out of the Einstein metric and these phonons, right? So these phonons mediate or modify the space-time experienced by test particles, light rays, rods, and clocks in galaxies. As far as those are concerned in galaxies, they only see the effective metric in the ways described earlier, and the Einstein metric, they don't directly see this, right? So first conclusion, it's much more to unpack here, but first conclusion is that the new field postulated by superfluid dark matter is as much dark matter as it could be, and also, at least in the superfluid regime, a modification of space-time. So where to go from there? How should we philosophically interpret such a theory? Does this mean just what is written here? Does it mean that maybe it's really dark matter and only acts as if it's modified gravity, is kind of a modified gravity imposter in certain regimes, or the other way around? Or maybe this means we should stop talking about this distinction because it's just not very helpful here anymore. So to get some grip on those questions, let me just mention 3 groups of possible interpretations, which I think are good to keep in mind when trying to understand what such hybrid theories tell us about the world, or about the world they would describe if true. So here's option 1, with a somewhat ugly name, consubstantiality interpretation. Right, so whereas I am 100% human and not at all divine, Zeus is completely divine, not human. Then you have Heracles, which is a demigod, 50% human from his mother Alcmene, and 50% god from his father Zeus. And according to the consubstantiality interpretation in Trinitarianism, right, a version of Christianity, Jesus is both fully human and fully divine. So the idea of this interpretation, by analogy, would be that we interpret this new field as both being fully dark matter, fully a modification of space-time. Both these aspects of this field are on a par, and nothing more needs to be said, right? This leaves the conceptual categories of dark matter and modified space-time untouched. It leaves them coherent, applicable, objective, useful. And just as the fact that Jesus doesn't, because Jesus is in some sense an anomaly, he's the only person, the only entity that's human and God, that doesn't mean we should stop using the categories human and God. Similarly here, if this is this kind of an exception, is this one theory or a few theories which are hybrid, this doesn't, according to this interpretation, we say, okay, that doesn't mean much. We can still, most cases, the concepts dark matter and modified gravity are still very useful. Now, there's a second group of interpretations which would basically say, no, there's something more we can say. It's not just we should be quiet, just accept it's both dark matter and modified gravity. That's the end of the story. Right? So you might want to say maybe one aspect is more important than the other, right? And importance, of course, is a bit of a vague subjective word. So one way of cashing that out is saying, well, maybe one of these aspects is fundamentally a fundamental aspect of this new field, and another aspect is only an emergent or derivative aspect, right? I mean, in kind of the formal sense in which philosophers or metaphysicians use it, right? For instance, in the sense that the emergent entities, properties, etc., are ontologically dependent, so they can only exist in virtue of the fundamental stuff and not the other way around, right? So kind of the emergent stuff is an approximation that depends on the fundamental stuff for existing, but not the other way around. So prima facie, that leaves 4 possibilities, right? 2 by 2. It could be that the dark matter aspect, the massiveness of this field, is fundamental property of the new field, or just a derivative property. Similarly, the modified gravity aspect could be fundamental, or could be merely emergent, non-fundamental derivative. So this gives 4 possible interpretations. Now, which of these to go for? Well, the problem there is that the theory is not fully complete yet, so that's somewhat problematic. However, we know that in a complete superfluid dark matter theory, the new field being postulated will be massive. So the dark matter aspect seems to be a fundamental aspect of a theory. So that will bring us in the top half of this table, right? Dark matter is fundamental, but is the modified gravity aspect also fundamental? Is it equally important, or is it just a kind of derivative? Is it just a modified gravity imposter? And is this really at base level a dark matter theory? So it's somewhat, well, could go both ways, right? So for instance, you might say, well, the modified gravity aspect is only an emergent, an effective, an approximate property aspect because it's only the case in galaxy, right? It's not everywhere. The scope for where we can apply this modified gravity description is not universal. It's only in galaxies. So it's emergent. It's not part of the fundamental theory. So the problem there as well, presumably this theory, when it's complete, is going to say that outside of galaxies, the modification reduces to 0. So it's not saying that the theory is not applicable outside of galaxies. It will just say well, that's just where it coincides with normal GR, with dark matter, right? There are other fields we know which are sometimes zero, like, right, the electric field in the Faraday cage, the magnetic field in a very long solenoid. We don't suddenly say, oh, the value is zero somewhere, so it's not a fundamental field. Also, in this theory, the dark matter aspect and modified gravity aspect are different phases of the same entity, right? So if you would say, well, one is the fundamental aspect and the other one is merely derivative, that's a bit like saying, oh, water is fundamentally ice and only emergently liquid water, right? That seems very weird to say. These are just different phases, different states of being of one entity. It seems weird to say that it's fundamentally ice or not. Similarly, you might think, okay, well, the reason why you might think modified gravity is just an emergent aspect is not because it only applies in the center of galaxies and nowhere else, but because it's a limiting theory, right? It's an approximate theory, which is derived from the full theory, which applies everywhere, from some irreversible mathematical operation like coarse graining, and that's why it's only an approximate emergent non-fundamental description. However, as Alex Franklin and Eleanor Knox have pointed out in a recent paper, and when you look at phonons in crystal lattices, that's actually not the case that the phonons are arrived at from a coarse-grained, irreversible mathematical description. There's actually a duality between the phonon description and the particle description, so you can always translate back and forth without loss of information. So it's not obvious that one of these is more fundamental than the other. They're equally valid and descriptions which can be fully translated into each other. You might also think, well, maybe it's fundamentally dark matter and emergently modified gravity because there is a fundamental way of telling the story which only mentions the massiveness of this field, and then there's a story we tell in galaxies where we only use this phonon story. But again, I mean, it's a bit problematic here because the final theory is not totally given. Part of the theory are a bit phonological, but it seems that you always have some effect from the mass. The mass is always there, so this can always influence the metric, right? But nonetheless, the phonons will also always couple directly with the baryon. So it seems you always just have a mixture of both explanations going on. It's just in some regimes, one is way more important, quantitatively speaking, but they're both going on. So it seems it's not obvious that you can say, well, modified gravity is just an emergent aspect. So both of these options on the top are still available, I'd say. Then one, I'll start wrapping up. One final group of interpretations would be, let's stop talking about which one is more important than the other. The fact that we have now these hybrid theories, which are both matter, both space-time, shouldn't they tell us that we should stop talking about the space-time matter distinction, about the distinction between dark matter and modified gravity? Shouldn't we just forget about that distinction altogether? Right, so the various versions of this interpretation, you could say, well, maybe this shows us that these concepts were incoherent. That's, for this theory, probably too strong. You might think they're coherent, but it's inapplicable. Again, that seems too strong here because, well, one of the earlier conclusions was, no, this field it's coherent to say this field is both fully matter and fully modified gravity. I think, okay, maybe it's just a conventional matter, right? For instance, there are theories in the case of dark energy, where you have things like FFR gravity and Jordan's Bernoulli theory, which are kind of dual to each other. You can, via coordinate transformation, go back and forth. If you think FFR gravity is really gravity, and if you think that the scalar field in Jordan's Bernoulli theory is a matter field, then it seems just a change of description, a change of coordinates, whether it's called as a matter theory or a space-time gravity theory. So that just seems to be conventional. Again, it's probably too strong for the theory I've been talking about now. Nevertheless, I think a weaker version of the breakdown interpretation would be viable, where you say, well, you can use these concepts, dark matter, modified gravity, but for such a theory, it's not clear that they do any work. Why would you use them? They're dispensable, right? So you might have thought these things are important because they neatly separate objects in our universe. Well, that's not the case here. You might think, well, these concepts are important for the substantialism relationism debate in philosophy of physics, right? Again, it's not clear anymore that it makes sense here, right? That debate is all about, is space-time relatively fundamental compared to matter? But if this object instantiates both categories, it's like saying, is it object fundamental with respect to itself? It's not clear that that means anything at all. So I think this is one way of going about it, saying that these categories are just not that important to you anymore. Why they don't do any work? Let's move on. Now, there's much more to say here, and my point is not really to convince you of there being one best interpretation. Part of the reason for that is that the theory still needs to be developed further. But what I want to say here is that there are all these options on the table for such hybrid theories, and different hybrid theories might have different options that work better. And the main idea here is to say, well, we should be a bit more open-minded, broaden our horizon. Once we look into these hybrid theories, there's much more room for thinking about such very basic concepts such as matter and space. So I think the four green ones are still viable. So let me just get to the upshots. I think a few things we learned from this is I think we should realize that there's really a single space of theories, right? So if you think there's only a space of dark matter theories and of modified gravity theories, a separate one, this hybrid theory is not going to fit neatly into one of these. So it seems we just have one big space where one region is kind of the dark matter region, maybe. There might be another region which is purely modified gravity, but there are also unexplored regions which kind of fall in between in various ways. Also, substantialism relationism debate, loads of papers on this in the philosophy of physics literature. It's not clear that especially if you go for some breakdown interpretation, that this still makes a lot of sense when you look at such hybrid theories. And then finally, to get back to kind of picture I sketched at the beginning, right? Trying to understand the relationship between the communities, why it's so hostile, why they don't get along. As said, it seems part of the reason seems to be that they really think only one theory can be right. Either you postulate something that's dark matter. If you do so, and that explains the data. That must be modified gravity is incorrect because these two things cannot overlap in any way. They cannot. They are mutually exclusive things. And I think such hybrid theories such as this one show that that's not necessarily the case, right? It could well be that we have a theory which vindicates both camps. So in that sense, it might be that such hybrid theories could play a role in fostering it. I don't know if trading zone or boundary object is the right word here, but something that allows both camps to talk to each other, to coordinate, to communicate. Because a few years ago, we had a big conference in Aachen where we got loads of physicists on the dark matter side and on the modified gravity side. And whenever there was a clear talk, there was a clearly dark matter talk, the modified gravity people were really not liking it, really critical, and the other way around. And then only when we got the talk about hybrid theories, then all of a sudden, that was the only talk that was appreciated by both camps. Probably that's because they attach different meanings to such theories, right? Where the dark matter people might have thought, oh, this is really dark matter. So yes, this shows we're doing well. And it kind of acts a bit like modified gravity. Whereas the modified gravity people hear the same talk and like, oh, this really modified gravity, this vindicates us. So they might still have attach different meanings and different interpretations to this theory, but that's totally fine when you're trading. It doesn't mean that the value and the meaning must be the same to all groups, but at least there's a way for them to come together and communicate and collaborate. And I had one more slide, but since I've run out of time, let me stop there. Other than to say, you can ask similar questions about different contexts and in different contexts. One of these is, of course, black holes. Are black holes best understood as material objects or space-time? Well, vacuum solutions to GR. And this is something I hope to look at next year when I'll be a BHI fellow. But let me just stop there for now, and thank you for your attention.
How are you going to do this?
I know you have a question, but you also, are you the ceremonial director of questions, or do you want me to do it?
Sorry, I missed the beginning of that. Were you talking to me?
Are you going to field the questions? Are you going to?
I certainly can. We usually start with questions in the room. So if you want to go ahead, then.
No, Ramesh has a question. I thought you had a question. So I just want to know who's directing.
Ramesh, why don't you go ahead?
Yeah, no, very interesting talk.
Thanks.
So I'm just kind of recalling the history of this thing. All started with flat rotation curves being inconsistent with the distribution.
Sorry, I don't understand very well.
Yeah, you're cutting in and out a little bit. Perhaps you could.
Can
we get this microphone to work? That would be great.
Yeah, just a second, please. I can go there.
The hybrid is just that much more technologically difficult to manage than either in person or Zoom.
Can you hear us?
I can certainly hear you, Nicole.
You hear me? Maybe I should just come there.
Yeah.
You want to spend, right?
No, just last week was in India.
Yeah, it's still sort of cutting in and out. I wonder if you could use the webcam microphone. That tends to work well.
Okay. Sometimes I just want to rip this whole system out.
I know.
Okay, how about now?
I can hear you.
You just heard that.
I'm going to come late at night with a crowbar.
Okay.
She can hear, right?
Yeah. Okay.
Are you serious?
This is fixed.
Okay, we can hear you, Jamie. Can you hear me?
I can hear you right now, yes.
Okay.
Okay.
We can't hear Ramesh right now.
Can you just type it into the chat for Niels if he can't hear you?
I think we can have just this, people on the screen ask questions.
Okay, Jamie, go ahead and ask your question, Jamie.
I mean, I didn't really have a question, but I can come up with one on the spot if there's nobody else who had a hand raised.
Ask the computer to Ramesh, and he can just talk into it.
Okay, well, it's all plugged in over
I
here.
see.
I can come there.
Yeah.
But they were not able to hear me even then.
It's very bizarre. The microphone seems to sometimes be working and then it just cuts out. So hopefully, yeah, if you stand by the computer, it'll be fine.
Well, I mean, we've had this in Bonn as well. I think that some computers, lower voices are filtered out much more.
You should recall towards Ramesh.
How about now? You hear me?
No.
Good. Okay. So I'm just looking. Okay. Okay. Struggle with this.
Yeah, this was good. You know, maybe we do it.
So I heard nothing. I don't know if.
Computer and log in and proceed.
So Niels, you said that at the conference that you had, like the talks about hybrid theories seemed to be some kind of building some kind of trading zone to some extent. But that, I mean, I think that was before you wrote this paper with Dennis. Is that right?
Yes.
Mm-hmm. So I guess I'm interested what you think the prospects are moving forward. You know, do you think that the kind of this kind of, I guess, taxonomy of different interpretations? Is this something that you've seen people in these two communities? Do they seem to like it, or do they seem to be very resistant? Because I can see that having it pointed out that they were being dogmatic and that they needed to be sort of seeing each other as seeing themselves as really different versions of the same kinds of theories might not go down so well, or it might be very productive. I don't know.
Well, I didn't mean to say that this talk is going to completely change the dynamics between. I think, no, I mean, I guess the honest answer, as I said, I mean, it was more like a hope that if there is a chance that there will be a training zone, or that this could function as, I don't know, if training zone of a boundary object would be the best way of describing such a theory. But what I have noticed, although this is also somewhat further back, is like, so one way of understanding what's going on is dark matter versus modified gravity, and that tends to be very problematic. Another way of understanding what's going on is there's one community, a cluster of communities, dark matter community, and then there are observational astronomers, some of which like dark matter, some of which like MOND, and as long as they don't use the word MOND and just mention certain astrophysical correlations, right? As long as the word MOND isn't there and there's no talk about conspiracy theories, etc., then it seems to be much more fruitful interaction. So I think the Mondians have to some extent, but already kind of a while back, understood this, and they've started reframing. So some would say initially like, oh, we should interpret it as a force, etc. Actually, in fact, Milgram never did this from the start. He said it's an effective theory, we still need to find the underlying thing. But people like Saunders and Stacey McGaw, like some of the other most prominent sympathizers with the theory, started realizing that using MOND, especially as a theory or a force, is not helpful. So they are talking about now in terms of, for instance, an algorithm which allows you to predict from the baryonic input what's going to be the observable output, etc. So they're kind of rephrasing things in a more neutral way. I think because they think that might be more useful if you want the other side to listen. This might help a bit, although perhaps it's also to some extent too late, in the sense that it would have been great if this would have been done for the start, but maybe depending if you used this phrasing in terms of people who've been familiar with MOND for a long time, it's not going to change anything, but it might help if people who come into contact for the first time with MOND and they see that, oh, it's an algorithm. So for nowadays, Stacey McGaw is mainly phrasing in this. The puzzle is for dark matter to explain why MOND as an algorithm get anything right. Why not necessarily tell us that there is a modification of Newtonian gravity. Why could we summarize much of the astronomical data in terms of this algorithm or this neat thing which doesn't seem to mention dark matter necessarily? But yeah.
Shall I type it and see if I can be heard? Can you hear me, Niels?
Yes.
I think you can hear me through Ramesh's computer, probably. No, this is Priya. Sorry, very nice talk. I missed a bit of it and I was out. But, one of the reasons the traditional astronomers have been very resistant to MOND is that clusters of galaxies, right, the largest repositories of dark matter in the universe, and the gravitational lensing that is seen, MOND cannot explain it. In order to account for lensing, MOND theories need another unseen component, like, sterile neutrinos or something else. So I think part of the astronomer's sort of pig-headedness has to do with that. It's hard to be open because we have a fundamental belief that a theory that works on galaxy scales ought to work on larger scales as well, because, we are used to a scale-free theory, right? So, and I think that's part of the resistance. And you're right. I think you're absolutely right that McGaw, Benoit Famé, Saunders, these people are reframing and not using that word and trying to see, because it is interesting. The phenomenology that they can explain alternatively is interesting, for sure. So.
Yeah, no, I totally agree. Like, it's very difficult for me not to be right. So I said the first part of the story is the empirical part of the story, And when I say that I think there is some value offered by both sides, I'm totally aware of everything you just said. And yes, there are very big problems. If you want the current MOND or some extension to explain everything, you have lots of problems, although we had Tevis, and then of course they run into problems with the LiGO results. And now we supposedly have this new theory by Skordis and Schlossnik, which some have just called a more baroque form of dark matter. There are many problems, and you're probably right if that's what you were saying, that MOND has many more problems, and I'm not sure how to quantify this, but the main thing, I think, right, if you think of science as this, right, as Peter likes to talk about it, is kind of web of different communities which coordinate the trading zones, and that's what ensures that there's progress in science. By saying both sides have something to offer, I didn't mean to say or deny that MOND has any chance at being correct as a force or modification of gravitational structure as being universally true. That's why I need to also try to direct towards the community of observational astronomers, draw attention to like the Renzer's rule, Faber-Jackson relation, to the baryonic to the Fisher relation, which we don't even have to mention MOND. It's just interesting that MOND nicely summarizes those results. So I think that value or their emphasis on these things is enough to for it to be useful if there was a better communication between these two communities, without that saying that we should in the end have a decent chance at ending up with MOND at the win. It's exactly because this opens up room for, maybe there are theories which take the best of both worlds. And maybe you think superfluid dark matter theory really is dark matter for all the reasons you mentioned and all the reasons physicists have mentioned very often. But nevertheless, we can very easily, because if it's a boson, it's going to be, if it's a boson and it's repulsive, then it's going to have a critical superfluid temperature. And if it's such that it happens in the core of galaxies, you don't need to put on something extra, right? If you have bosonic dark matter like an extra, you're going to get this Bose-Einstein condensate, and then you see, well, what does it do? So if it then neatly kind of gives us the few things that dark matter was missing, I would say, well, that will be great, and that is something which has been resisted too much because that kind of these phenomena are associated with the Mondians. Okay, I think I'm going to stop talking there.
Well, thanks for the clarification.
Ramesh, do you want to try again?
Okay. Does this sound okay?
Turn your computer volume down.
You want me to turn my volume down?
Yeah.
Just the volume. Not the microphone off.
How about now?
Turn your microphone off too.
I think he needs the microphone, but just turn,
Something is wrong with my voice.
Just turn your sound off.
Okay. Okay. Niels, thumbs up. Great. Thank you. So Niels, there was this problem with the flat rotation curves. Mm-hmm. It couldn't be explained with normal gravity and just baryonic galaxies. So we needed to change something. We needed a tooth fairy, right? So MOND came with its tooth fairy, which was to modify gravity. And then they said, I can do it with baryons, but I'll just change gravity. And then the dark matter people came and said, no, I won't change gravity, but I will invoke a new kind of matter. I think both guys were successful up to a point. And in fact, the cold dark matter people tell me they really have explained it all. So when we now look at this superfluid model, which is, to me, looks like just another flavor of dark matter, all that one is doing is you're changing some of its properties at smaller scales to fix a few of the problems. But other than that, it's still in the camp of the dark matter, it seems to me. So in what sense is it an amalgamation of the two? Because to me, at least in your 2x2 matrix, this model seems to sit definitely top right. You can interpret it if you wish as some emergent property at smaller scales, call it MOND, but it's really a dark matter model. Isn't that what it is? What am I missing?
With the top right, you mean that both dark matter and MOND are fundamental? Is that?
I think it's just a dark matter model.
Yeah. Yes. Well, yeah. Okay. I mean, yes, that's kind of what I also think. But it's kind of so. Yeah. So. Yes, when I said there are 4 viable interpretations left, that is partially to be conservative and because the theory is not fully done and because I have a co-author, of course. But yeah, one of my favorite, yes, I tend to think of it as being both equally well. And I can think because of that, if it's just kind of a bit of both, that or both 100%, both fully, then this kind of gives me even more reason to think, why are we still talking about these two concepts as separate? It is just both at the same time, and these concepts were useful in the past because we only, right? It's a bit like, imagine we had lived in a world where we only saw blue things that were squares and squares that were blue things, and only red things that were circles and circles that were red things. And we might come up with 2 different names for those, right? Blah and blah, and use those. And then after a while, suddenly we encounter something which is blue and circular. And then we're like, oh, okay. Now it just turns out that these earlier concepts were not very useful. They just seem to coincide for no reason. Maybe we should stop using them, unless there's only kind of one exception, then it's still practical to keep using these. But if you then, yeah. So yes, I kind of agree what you were saying. And I would then add to that, well, this seems, I want to stop insisting, yeah, that this means it just isn't an amalgam, it's kind of both. So maybe let's just stop using both terms altogether, or at least if there are more hybrid theories like that. But that's kind of the thing, right? These communities don't like to do that. So I think if they had not been so hateful of the other side, these hybrid theories might have come along much earlier. And not that that necessarily would have changed everything, but who knows what else we're missing by, yeah. So basically what you're saying is, yes, I would hope the attitude you just displayed would be what more physicists from both sides would do. And maybe we kind of get less stuck and lead to unexplored regimes. But yeah, I very much sympathize with what you said.
Peter?
Can you hear me?
Mm-hmm.
So presumably the 2 communities are both represented, although in different proportions, in the astrophysical world. But there are also particle physicists at accelerators who study dark matter. And, you know, the Padme experiment, many others, calorimeter experiments, and so on. Those are people who, you know, whose lives don't include gravity very much, right? They're particle accelerator physicists and they're experimentalists. Do they weigh in on this debate of the hybridity, or are they purely on the side of a particle physics, container like?
They're wind fixated. All the searches so far have been wind fixated. And only now they've moved to sort of axions, so lighter dark matter candidates. So I think the consensus there is CDM maps on very nicely to wind, because you get the right omega with the wind to account for omega dark matter. So that fixation is very much there. But if they've come up empty, you're right, for 20, 30 years.
There are all these, something that I worked on in my misbegotten youth was a second Z that you can have, a massless Z that Manohar and I wrote about, and that's figured in a lot of these particle experiments. I don't know whether, the Z photon like that, but I don't know all of that literature at all. This is from ancient history. Hey. Hi. We can talk more about it offline.
So I'm not sure I heard all of that, but
I just wondered how the accelerator physicists who are looking for dark matter figure in the debate that you've been discussing.
Dark
matter searches at accelerators like the Padme experiment or NA64 or the various other ones. Anyway, we can talk about it later.
I think this relates to the digital humanities project we're working on. So by the time I'll see you next time in person, we might have some nice co-citation analysis to help you answer this question.
Thank you very much. Thank you for a great talk.
Yeah, thanks for a great talk.
Thanks.
Thanks, Niels. Thanks, everyone. See you.